Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. The universe is filled with motion, and within that motion, there is a tendency towards something that scientists describe with precision as rotation, which is a type of movement that can be observed across many scales, from the smallest particles studied in laboratories to the largest structures visible through telescopes. And this rotation is not a mysterious force or an unexplained phenomenon, but rather a predictable outcome of fundamental physical laws that have been studied carefully, measured repeatedly, and described mathematically over many generations of scientific observation. When scientists refer to spinning or rotation, they are describing a specific type of motion in which an object turns around a central point or axis, much like a wheel turning around its center, or like water swirling slowly down a drain, or like a figure skater rotating with arms extended. And this motion can occur at different speeds and with different characteristics, but the underlying principle remains consistent across all examples, which is that rotation involves movement in a circular or curved path around some reference point. To understand why rotation appears so frequently throughout the universe, it helps to begin with very simple everyday observations that anyone can make without specialized equipment or advanced training, because the same physical principles that govern the motion of galaxies also apply to objects that we encounter in daily life, such as a spinning top on a table, or a bicycle wheel turning steadily, or a merry-go-round at a playground, rotating slowly under the weight of children. And in each of these cases, the rotation continues for a period of time, according to laws that can be described with mathematics and tested through repeated experiments. The concept of angular motion, which is the scientific term for this type of rotational movement, describes how objects move in paths that curve back upon themselves, rather than traveling in straight lines. And this curving motion follows patterns that have been studied extensively by physicists and astronomers. Over centuries of careful observation and measurement, when an object rotates, it possesses what scientists call angular momentum, which is a quantity that describes both the speed of rotation and the distribution of mass within the rotating object. And this angular momentum behaves according to specific mathematical rules that have been verified through countless experiments and observations, remaining consistent whether the object in question is a spinning coin on a desk or a spiral galaxy containing billions of stars. The law of conservation of angular momentum states, in very simple terms, that the total amount of rotational motion in a closed system remains constant unless acted upon by an external force, which means that once rotation begins, it tends to continue, and this principle can be observed in many familiar situations, such as when a figure skater pulls their arms inward during a spin and rotates more quickly as a result, not because they are adding energy, but because the angular momentum is being redistributed across a smaller radius, causing the rotation rate to increase in a predictable mathematical way. This conservation principle operates over extremely long timescales in space, where there is very little friction or resistance to slow down rotating objects. And this means that rotation, once established, can persist for billions of years without diminishing significantly, which helps explain why we observe rotation throughout the universe in structures of all sizes and ages. To understand how rotation begins in the first place, it is helpful to consider the behavior of very small particles and clouds of gas and dust in space, which are the building blocks from which larger structures eventually form over immense periods of time. These particles and clouds are not perfectly still, even in the emptiness of space, because they possess small amounts of motion in various directions, some moving slightly to the left, others slightly to the right, some moving upward or downward. And these tiny motions, which may seem insignificant when considered individually, can accumulate and combine according to mathematical rules that govern the addition of vectors, which is the scientific term for quantities that have both magnitude and direction. When many particles or small clumps of matter interact through gravity, which is the attractive force that exists between any two masses, their individual motions begin to average out in certain directions while reinforcing each other in other directions, and over very long periods of time, measured in millions or billions of years. This gradual process can result in a net rotation of the entire cloud or collection of particles. The process occurs very slowly, without any sudden changes or dramatic events, simply as a natural consequence of gravity pulling particles together while preserving their individual motions. And because the particles rarely have motions that perfectly cancel each other out in all directions, there tends to be some slight residual motion that manifests as rotation once the particles begin to form a more concentrated structure. Gravity itself does not create rotation directly, but rather causes matter to move inward toward regions of higher density. And during this inward motion, the particles carry with them whatever sideways or tangential motion they originally possessed. And this sideways motion becomes more pronounced as the particles move closer together, much like water circling faster as it approaches the drain in a bathtub. As clouds of gas and dust in space slowly contract under their own gravity over millions of years, they gradually flatten into disk shapes. And this flattening occurs because rotation causes the material to resist collapse in the directions perpendicular to the axis of rotation, while allowing collapse to continue more easily in the directions parallel to that axis, resulting in a disk structure that can be observed in many astronomical objects, from newly forming star systems to mature spiral galaxies. Within these rotating disks, smaller concentrations of matter continue to form, and these smaller concentrations inherit the rotational motion of the larger structure from which they form, which explains why planets rotating around stars and moons rotating around planets all tend to move in the same general direction, following patterns that reflect the original rotation of the cloud from which the entire system formed. Billions of years ago, stars themselves acquire rotation through the same gradual process, forming from regions within larger clouds where gravity has caused matter to concentrate, and as the matter falls inward toward the center of the forming star, it brings its angular momentum with it, resulting in a star that rotates around its axis, sometimes quickly and sometimes more slowly, depending on the specific conditions present during its formation. The rotation of a star can be measured by observing features on its surface, moving from one side to the other over a period of days or weeks. And these measurements confirm that stars do indeed rotate in ways that are consistent with the conservation of angular momentum and other fundamental physical principles. Planets form in the disks of material that surround young stars, and as they gradually accumulate mass from the surrounding material, they too acquire rotation, both in the sense of spinning around their own axes and in the sense of orbiting around the central star. And both types of motion can be traced back to the initial conditions present in the cloud of gas and dust from which the entire planetary system formed. Nearly every object that has been observed in space exhibits some form of rotation, whether it is a small asteroid tumbling slowly through the solar system, a planet spinning steadily on its axis, a star rotating at its equator, a binary star system in which two stars orbit their common center of mass, or an entire galaxy containing hundreds of billions of stars, all moving in coordinated patterns that reflect the overall rotation of the galactic structure. This near-universal presence of rotation is not a coincidence or a mystery, but rather a direct consequence of the way physical laws operate. When matter interacts through gravity over long periods of time in the relatively empty environment of space, where friction and resistance are minimal, and angular momentum can be preserved with very high accuracy across billions of years, galaxies, which are among the largest structures in the universe, also rotate, and this rotation can be measured by observing the motion of stars and gas within the galaxy using instruments that detect small shifts in the wavelength of light due to the Doppler effect, which causes light from objects moving toward us to shift slightly toward shorter wavelengths, while light from objects moving away shifts toward longer wavelengths. These measurements reveal that galaxies rotate in an organized fashion, with material farther from the center, typically moving more slowly in terms of orbital speed than would be expected based on the visible matter alone, which has led scientists to infer the presence of additional matter that does not emit light, commonly referred to as dark matter, though the rotation itself is still governed by the same fundamental principles of angular momentum and gravitational attraction that apply to smaller systems. The rotation of galaxies develops over billions of years as matter gradually collapses and organizes itself under the influence of gravity and the specific rotation rate and pattern depend on the initial distribution of matter and motion in the region where the galaxy forms, which varies from one location to another in the universe, but always follows the same underlying physical laws. In the very early universe, shortly after the period known as the Big Bang, matter was distributed with slight variations in density from one region to another, and these variations were very small, typically only a fraction of a percent difference in density. But over billions of years, gravity amplified these small differences, causing regions of slightly higher density to attract more matter and grow even denser, while regions of lower density became relatively emptier. The matter in these denser regions did not fall directly inward in perfectly straight lines, because the universe is three-dimensional and matter has motion in multiple directions simultaneously, and these motions, even when very small, result in angular momentum that is preserved as the matter collapses, leading inevitably to rotation in the structures that form. The process can be understood through analogy with a very large group of people walking randomly across a field where each person moves in a slightly different direction at a slightly different speed. And if this group were somehow drawn together by an attractive force, their individual motions would not all cancel out perfectly, and the resulting crowd would likely have some net motion in one direction or another, manifesting as a slow rotation of the entire group around some central point. Mathematical models that describe rotational motion use concepts such as angular velocity, which measures how quickly an object rotates, typically expressed in terms of radians per second or revolutions per minute, and angular acceleration, which measures how quickly the rotation rate changes over time, and moment of inertia, which describes how the mass of an object is distributed relative to its axis of rotation and determines how difficult it is to change that object's rotation rate These mathematical quantities are related through equations that have been derived from fundamental physical principles and tested extensively through experiments and observations, and they allow scientists to predict with considerable accuracy how rotating systems will behave under various conditions, from the precession of a spinning top on a table to the gradual change in the orientation of a planet's rotation axis over thousands of years. The conservation of angular momentum can be expressed mathematically by stating that the product of the moment of inertia and the angular velocity remains constant in the absence of external torques, which are forces applied in such a way as to cause rotation or to change existing rotation. And this mathematical statement captures the observation that rotation, once present, tends to persist and can only be altered by specific types of interactions with external objects or forces in space, where matter is separated by vast distances and interactions between objects are infrequent. The conditions for conserving angular momentum are met very closely, and this is why rotation in astronomical objects can remain stable for extremely long periods, changing only very gradually, if at all. Friction and resistance, which are familiar from everyday experience as forces that slow down motion and convert kinetic energy into heat, operate very weakly in the vacuum of space, where there is no air or other medium to create drag on moving objects. And this absence of significant friction allows rotating objects to maintain their rotation with very little loss of energy over time. In planetary systems, there are some sources of friction, such as tidal interactions between a planet and its moons, or between a planet and its parent star, which can gradually transfer angular momentum from one object to another and slowly change rotation rates over millions or billions of years. But these processes operate very gradually and do not significantly alter the basic fact that rotation, once established, tends to continue. Tidal forces arise because the gravitational pull on the near side of an object is slightly stronger than on the far side, creating a stretching effect that can cause internal friction within the object as different parts move relative to each other. And this internal friction gradually converts rotational energy into heat, which is then radiated away into space, causing a very slow decrease in rotation rate over geological timescales. The stability of rotation in astronomical objects has been confirmed through detailed observations spanning many decades, during which the rotation rates of planets, stars, and other objects have been measured repeatedly with increasing precision, and these measurements show that while rotation rates can change very slowly due to tidal effects and other interactions, the changes are gradual and predictable, following patterns that are consistent with the mathematical models developed by physicists and astronomers. For example, the rotation of the Earth is gradually slowing down due to tidal interactions with the Moon, causing the length of a day to increase by a very small amount each year, typically a few milliseconds per century, and this change has been measured using extremely precise atomic clocks and by studying the growth patterns in ancient corals and other geological records that preserve information about the length of the day in the distant past. Scientific instruments used to measure rotation in space include telescopes equipped with spectrographs, which split light into its component wavelengths and measure the Doppler shifts caused by rotation, allowing astronomers to determine how quickly different parts of a star or galaxy are moving relative to the observer. And these measurements can be made with high precision by comparing the observed wavelengths to known wavelengths of specific elements measured in laboratories on Earth. Other instruments include interferometers, which combine light from multiple telescopes to achieve very high angular resolution, allowing detailed mapping of rotating structures, and spacecraft carrying cameras and other sensors which can observe rotating objects from various angles and distances, providing three-dimensional information about rotation axes and rates. Repeated experiments and observations over many years have confirmed that the patterns of rotation observed in the universe are predictable and consistent with the fundamental physical laws that govern motion and gravity. And these observations include measurements of rotation in newly forming star systems, which allow scientists to study the early stages of the process by which rotation develops, as well as measurements of rotation in very old systems, which demonstrate that rotation can persist essentially unchanged over billions of years when external influences are minimal. The consistency of these observations across different types of objects and different epochs in cosmic history provides strong support for the understanding that rotation arises naturally from the combination of gravity and the conservation of angular momentum without requiring any special mechanisms or unexplained forces. Probability and statistics play a role in describing the motion of spinning particles at the microscopic level, where individual particles move according to the laws of quantum mechanics and statistical mechanics, and the behavior of large collections of particles can be predicted using statistical methods that describe average properties and fluctuations around those averages in a cloud of gas in space containing billions upon billions of individual molecules. Each molecule moves in a random direction with a speed determined by the temperature of the gas. And while the motion of any single molecule is unpredictable in detail, the average motion of large numbers of molecules follows predictable statistical patterns. And when these molecules interact through gravity and begin to form denser structures, their individual random motions contribute to the net angular momentum of the forming structure in a way that can be described using probability theory. Temperature and pressure both influence rotational behavior in various ways, with temperature determining the average kinetic energy of particles and thus affecting how quickly they move and how they respond to gravitational attraction and pressure, which arises from the collisions between particles, affecting how easily a cloud of gas can collapse under its own gravity. Higher temperatures result in faster particle motions, which can provide pressure support that resists gravitational collapse, while lower temperatures allow gravity to dominate more easily, and in regions where temperature is very low, such as in dense molecular clouds in space, gravity can cause matter to collapse and form stars and planetary systems over relatively shorter timescales. Though even these shorter timescales are typically measured in hundreds of thousands or millions of years, which is very rapid by astronomical standards, but still incomprehensibly long by human standards. The internal energy within planets and stars, which includes both thermal energy associated with the random motions of particles and gravitational potential energy associated with the arrangement of mass within the object, is related to rotation in several ways, with rotation affecting how energy is transported from the interior to the surface through processes such as convection, where hotter material rises and cooler material sinks in rotating cells that are deflected by the Coriolis effect, which is a consequence of rotation that causes moving objects to curve to the right in the northern hemisphere and to the left in the southern hemisphere on Earth. And similar effects occur in the atmospheres of other rotating planets and in the interiors of rotating stars. Scientific uncertainty regarding rotation and its causes reflects the inherent limits of measurement tools and the complexity of the physical systems being studied, rather than any fundamental gap in understanding the basic principles involved. And scientists are careful to distinguish between what is known with high confidence based on repeated observations and theoretical modeling, and what remains uncertain due to limitations in data quality or the incompleteness of current models. For example, while the basic mechanism by which rotation arises from the conservation of angular momentum during gravitational collapse is well understood and supported by extensive evidence, the precise details of how rotation is distributed within the interior of a distant star, or the exact rotation rate of a galaxy that is billions of light years away, may be subject to significant uncertainty due to the difficulty of making precise measurements at such great distances. The scientific definition of rotation has become more precise Over time, as measurement techniques have improved, and as theoretical understanding has deepened, with early observations of rotation limited to what could be seen with the naked eye or simple telescopes, such as the phases of the moon and the motion of planets across the sky, gradually being supplemented by more detailed observations using increasingly sophisticated instruments, and the mathematical description of rotation has similarly evolved from simple geometric models to complex equations involving calculus and differential geometry that can accurately describe rotation in three-dimensional space and predict how rotation changes in response to various forces and torques. The physical laws governing motion, including rotational motion, are believed to remain consistent across the entire observable universe and throughout cosmic history, based on observations that show the same patterns of motion and the same relationships between force, mass, and acceleration in distant galaxies as in our own solar system. And this consistency is one of the foundational assumptions of modern physics, allowing scientists to apply equations derived from experiments on Earth to predict the behavior of objects billions of light years away with considerable success. This consistency also extends across different scales with the same fundamental principles applying to the rotation of subatomic particles, which possess an intrinsic property called spin that behaves mathematically like angular momentum, even though the particles are not literally rotating in the classical sense, and the rotation of entire galaxy clusters containing thousands of individual galaxies. Scientific reasoning in the study of rotation involves a careful balance between observation and mathematical modeling, with observations providing the empirical data that any theory must explain, and mathematical models providing the framework for understanding why the observed patterns occur, and for making predictions about what should be observed under different conditions. When observations and models agree, this provides confidence that the underlying physical principles are correctly understood, and when they disagree, this indicates either that the observations need to be refined, or that the models need to be modified or extended to account for phenomena that were not previously considered. The history of studying rotation in astronomy includes many examples of both situations, with some early models being refined as more precise observations became available, and some unexpected observations leading to new physical insights, such as the discovery that galaxies rotate more rapidly than would be expected based on their visible matter alone, which led to the hypothesis of dark matter. The language that scientists use to describe rotation has become increasingly precise and technical over centuries of study, with specific terms being defined carefully to avoid ambiguity and to allow clear communication of complex ideas. And this technical vocabulary, while sometimes seeming unnecessarily complicated to non-specialists, serves the important function of ensuring that scientific ideas can be expressed unambiguously and tested rigorously through experiments and observations. Terms such as angular momentum, torque, moment of inertia, precession, and nutation each have precise mathematical definitions that specify exactly what is meant and how the quantity in question should be measured or calculated, and these definitions are agreed upon by the scientific community and taught consistently in textbooks and courses around the world. The rotation of objects in space occurs at many different rates, with some objects completing a full rotation in a matter of hours, such as the Earth, which rotates once approximately every 24 hours, while others rotate much more slowly, taking weeks or months to complete a single rotation, and still others rotate very rapidly, such as pulsars, which are rapidly spinning neutron stars that can complete hundreds of rotations per second, emitting beams of radiation that sweep across space like a lighthouse beam, producing regular pulses that can be detected and timed with extraordinary precision, using radio telescopes. The wide range of rotation rates observed in nature reflects the diversity of conditions under which rotating objects form and the various processes that can affect rotation over time. But all of these rotation rates, from the slowest to the fastest, can be understood within the same theoretical framework based on the conservation of angular momentum and the laws of physics in binary star systems, where two stars orbit around their common center of mass. The orbital motion itself is a form of rotation, with the two stars revolving around each other in paths that are typically elliptical, following Kepler's laws of planetary motion, which were originally derived from observations of planets orbiting the Sun, but which apply equally well to any system where objects interact through gravity. The rotation of such systems can persist for billions of years with very little change, as long as the stars do not lose significant amounts of mass or interact with other nearby objects. And observations of binary stars have provided important tests of gravitational theory and have allowed astronomers to measure the masses of stars with high precision by observing the details of their orbital motion. The rotation axes of planets are not always aligned with the plane in which they orbit their parent star, and the angle between the rotation axis and the orbital plane, known as the obliquity or axial tilt, varies from planet to planet, with Earth having an obliquity of approximately 23.5 degrees, which is responsible for the seasons, as different parts of the planet receive more or less direct sunlight at different times of the year. The obliquity of a planet can change very slowly over time due to gravitational interactions with other planets and the parent star, causing the rotation axis to wobble in a motion called precession, which for Earth has a period of approximately 26,000 years, meaning that the direction in space toward which the rotation axis points completes a full circle relative to the distant stars over this very long time scale. Asteroids and comets, which are smaller objects in the solar system, also exhibit rotation, and their rotation can be quite complex, with some objects tumbling chaotically rather than rotating smoothly around a single axis, and others rotating very rapidly due to their small size and the way they formed, or the collisions they have experienced. The rotation of these small objects has been studied by observing how their brightness changes over time as different parts of their irregularly shaped surfaces reflect sunlight toward Earth, and these observations can be used to determine both the rotation period and the approximate shape of the object, providing information about the history of the object and the processes that have affected it over the age of the solar system. The rotation of gas and dust in protoplanetary disks, which are the rotating disks of material that surround young stars, and from which planets eventually form, has been studied in detail using radio telescopes that can observe the emission from molecules in the disk. And these observations show that the material in the disk rotates in an organized fashion, with the inner parts rotating more quickly than the outer parts in a pattern that is consistent with Kepler's laws. And as the material in the disk gradually accumulates into larger clumps that eventually become planets, these clumps inherit the rotation of the disk material from which they form, which explains why all the major planets in the solar system orbit the Sun in the same direction and in roughly the same plane. The Coriolis effect, which was mentioned earlier, is an important consequence of rotation that affects the motion of objects on rotating surfaces, causing moving objects to follow curved paths rather than straight lines. When viewed from the rotating reference frame, and this effect is responsible for many familiar phenomena on Earth, such as the rotation direction of hurricanes and the tendency of large-scale air and ocean currents to curve rather than flowing in straight lines. The Coriolis effect can be understood mathematically as a consequence of the fact that different parts of a rotating sphere move at different speeds, with points near the equator moving faster than points near the poles, because they trace out larger circles in the same amount of time. And when an object moves from one latitude to another, it carries with it the eastward velocity appropriate to its original latitude, which may be greater or less than the eastward velocity of the surface at its new latitude, resulting in an apparent deflection to the right or left, depending on the hemisphere. Gyroscopes, which are devices that use rotation to maintain a stable orientation in space, demonstrate another important property of rotating objects, which is that they resist changes to their axis of rotation, a phenomenon known as gyroscopic stability or rigidity in space. And this property is exploited in navigation systems for ships, aircraft, and spacecraft, where gyroscopes help maintain accurate measurements of orientation even when the vehicle is accelerating or turning. The stability of a rotating gyroscope can be understood through the conservation of angular momentum, which requires that any change in the direction of the rotation axis must be caused by an applied torque, and in the absence of such torques, the rotation axis maintains its orientation relative to the distant stars, providing a stable reference direction. The study of rotation extends to the quantum mechanical level, where elementary particles, such as electrons, protons, and neutrons, possess an intrinsic property called spin, which contributes to the angular momentum of the particle, even though the particle is not literally spinning in the classical sense of rotating around an axis. Quantum mechanical spin is a fundamental property that is quantized, meaning it can only take on certain discrete values rather than varying continuously, and it plays an essential role in determining the behavior of atoms and molecules and the properties of materials. The total angular momentum of a system must include contributions from both the orbital motion of particles and their intrinsic spin, and both contributions are conserved according to the same fundamental principles that govern the conservation of angular momentum at larger scales. Rotation continues to be an active area of scientific research, with ongoing observations of rotating objects throughout the universe, providing new data that can be used to test and refine theoretical models, and with new instruments and techniques allowing measurements of rotation with ever-increasing precision and in ever more distant or exotic systems, such as the rotation of supermassive black holes at the centers of galaxies, which can be inferred from observations of the material orbiting around them, and from subtle effects on the radiation emitted by that material. The rotation of a black hole is described by a parameter in the mathematical solutions to Einstein's equations of general relativity, and this rotation affects the structure of spacetime around the black hole in ways that can potentially be observed through their effects on nearby matter and radiation. The rotation observed throughout the universe, from the smallest particles to the largest galaxies, is thus not a mystery requiring special explanation, but rather a natural and inevitable consequence of the fundamental physical laws that govern the behavior of matter and energy, particularly the law of conservation of angular momentum, combined with the attractive force of gravity and the three-dimensional nature of space, which together ensure that matter in the universe, starting with tiny random motions and slight asymmetries in the early universe, gradually organizes itself into rotating structures over billions of years through processes that can be described mathematically and tested through observation. This understanding has been built up through centuries of careful observation, theoretical work, and experimentation, and it continues to be refined as new observations are made, and as our mathematical and conceptual tools become more sophisticated. But the basic principles have been established with high confidence and have been verified in countless different contexts from laboratory experiments with rotating objects on Earth to observations of the most distant galaxies visible through the most powerful telescopes, all showing the same consistent patterns that confirm our understanding of how and why rotation arises and persists in the universe. The accumulation of matter into rotating structures occurs through processes that operate continuously over timescales that are difficult for human minds to fully comprehend, with changes happening so gradually that they would be imperceptible, even if observed over many human lifetimes. Yet when considered over millions or billions of years, these slow changes result in the formation of complex rotating systems that can be observed and studied in various stages of development throughout the universe. When astronomers observe distant regions of space, they are seeing light that has traveled for millions or billions of years to reach Earth, which means they are observing these regions as they existed in the distant past, and by studying objects at different distances and therefore different epochs in cosmic history, scientists can piece together a picture of how rotating structures form and evolve over time, much like studying trees of different ages in a forest allows one to understand how trees grow and change throughout their lifespan. The mathematical description of rotation involves coordinate systems that specify the orientation of objects in three-dimensional space, and these coordinate systems must be chosen carefully to make the mathematics as simple as possible while still capturing all the relevant physical information. And in many cases, it is useful to work in a rotating reference frame, which is a coordinate system that rotates along with the object being studied. And in such a reference frame, the object appears stationary, while the surrounding space appears to rotate. And this change of perspective, while not changing any physical reality, can make certain calculations easier and certain patterns more apparent. Working in rotating reference frames introduces apparent forces, such as the Coriolis force and the centrifugal force, which are not real forces in the sense of being caused by physical interactions between objects, but rather are mathematical artifacts that arise from the fact that the coordinate system itself is accelerating. Yet these apparent forces can be very useful in understanding and predicting the behavior of objects in rotating systems, such as the circulation patterns in planetary atmospheres, or the structure of rotating fluid bodies. The density of matter in space varies enormously from the extremely low densities found in intergalactic space, where there may be only a few atoms per cubic meter, to the extremely high densities found in the cores of stars, where matter is compressed to millions of times the density of water. And this variation in density affects how rotation develops and how it influences the structure of astronomical objects in regions of very low density. Gravity acts very weakly, and structures take very long times to form, while in regions of higher density, gravity can cause matter to collapse more quickly, leading to the formation of stars and planets over relatively shorter timescales. Though even these shorter timescales are measured in millions of years, the relationship between density and the strength of gravitational effects can be expressed mathematically through equations that relate the mass and radius of an object to the gravitational acceleration at its surface. And these equations show that more massive and more compact objects produce stronger gravitational fields, which can more effectively pull matter together and maintain rotating structures against the disruptive effects of thermal pressure and other forces. Observations of star-forming regions in nearby galaxies show clouds of gas and dust that are in the process of collapsing under their own gravity and fragmenting into smaller clumps that will eventually become individual stars. And these observations reveal that the clouds are rotating, with the rotation being measurable through Doppler shifts in the spectral lines emitted by molecules in the clouds. And as the clouds collapse and fragment, the rotation becomes more pronounced in the smaller clumps, following the principle of conservation of angular momentum. And this process can be followed observationally by comparing images and spectra taken at different times, though the changes are generally too slow to be detected over periods of months or years, requiring instead comparisons of observations separated by decades or more, or comparisons between different objects that are thought to represent different stages in the same evolutionary sequence. The transfer of angular momentum between different parts of a rotating system can occur through various mechanisms, including gravitational interactions, magnetic fields, and friction or viscosity in gaseous or fluid components. And these mechanisms allow rotation to be redistributed within a system, with some parts potentially spinning up while other parts spin down, though the total angular momentum of the system remains constant if there are no external influences in the formation of a planetary system. For example, angular momentum is initially concentrated in the rotating disk of material surrounding the young star, and as planets form from this disk material, they acquire angular momentum through their orbital motion around the star, while the star itself may lose some rotational angular momentum through magnetic interactions with the disk material, resulting in a redistribution of the total angular momentum among the star, the planets, and the remaining disk material. Magnetic fields, which are generated by the motion of electrically charged particles within conducting fluids, play an important role in the dynamics of rotating astronomical objects, particularly stars and planets with liquid or gaseous interiors, where convection and rotation can combine to produce what is known as a dynamo effect, generating and maintaining magnetic fields that can extend far into the surrounding space and affect the motion of charged particles in that space. The interaction between rotation and magnetic fields is complex and can lead to phenomena such as stellar winds, where charged particles are accelerated away from the star along magnetic field lines, carrying angular momentum with them and causing the star to gradually spin down over billions of years. And this process of magnetic braking has been observed in many stars and is thought to be an important factor in determining the rotation rates of stars of different ages and masses. The distribution of rotation rates among stars of similar mass and age shows a considerable spread, indicating that while the basic processes that produce rotation are common to all stars, the specific details of how much rotation any individual star possesses depend on the particular conditions present during its formation and subsequent evolution, including factors such as the initial angular momentum of the cloud from which the star formed, the efficiency of angular momentum transport during the formation process, and the strength and configuration of magnetic fields that may have affected the star's rotation over its lifetime. Statistical studies of large numbers of stars allow astronomers to identify trends and patterns in how rotation varies with stellar properties such as mass, age, and chemical composition. And these statistical patterns provide constraints on theoretical models of stellar formation and evolution, requiring that the models reproduce not just the average properties of stars, but also the observed range of variation in those properties. The precession of rotation axes, which was mentioned earlier in the context of Earth's axial precession, is a phenomenon that occurs when a torque is applied to a rotating object in such a way that the torque is perpendicular to the rotation axis, causing the axis to slowly sweep out a cone in space rather than changing the rotation rate itself. And this motion can be observed in many contexts, from the wobbling of a spinning top on a table as gravity exerts a torque on it, to the slow change in the orientation of planetary rotation axes due to gravitational torques from other planets and the Sun. The rate of precession depends on the magnitude of the applied torque and on the angular momentum of the rotating object. With more rapidly rotating objects, or objects with larger moments of inertia, precessing more slowly for a given torque, and these relationships can be expressed through mathematical equations that allow the precession rate to be calculated if the relevant properties of the system are known. Nutation, which is another type of motion that can affect rotating objects, refers to a small wobbling or nodding motion that is superimposed on the precession, causing the rotation axis to trace out a slightly wavy path rather than a perfectly smooth cone. And nutation typically has a shorter period than precession and arises from the same types of gravitational torques, but with variations in the torque that occur on shorter timescales. The Earth's rotation axis exhibits both precession and nutation, with the precession having a period of about 26,000 years, and the nutation having a principal period of about 18.5 years. And both of these motions can be measured with high precision using modern observational techniques such as very long baseline interferometry, which uses radio telescopes separated by thousands of kilometers to measure the orientation of the Earth with extreme accuracy. The rotation of galaxies is influenced by the distribution of matter within them, including both the visible matter in the form of stars and gas, and the dark matter that is inferred to exist based on the gravitational effects it produces, but which does not emit or absorb light in ways that have been detected. And the presence of this dark matter, which appears to be distributed in a roughly spherical halo around galaxies, affects the rotation curves of galaxies, which are graphs showing how The orbital velocity of material in the galaxy varies with distance from the galactic center in the outer regions of galaxies, where there is relatively little visible matter. The rotation curves remain flat or decline only slowly rather than dropping off, as would be expected if only the visible matter were present. And this observation is one of the primary pieces of evidence for the existence of dark matter, though the exact nature and properties of dark matter remain subjects of ongoing research and investigation. The rotation of molecular clouds, which are the densest and coldest regions in the interstellar medium, where stars form most actively, can be studied through observations of the emission from molecules such as carbon monoxide, which emit radiation at specific radio wavelengths. When the molecules undergo transitions between different rotational energy levels, and these emissions can be mapped across the extent of the cloud to reveal patterns of velocity that indicate rotation and other types of motion, such as expansion, contraction, or turbulent flows. The turbulence present in molecular clouds, which consists of chaotic motions on a range of size scales, from the size of the entire cloud down to very small scales, can affect how angular momentum is distributed within the cloud and can influence the fragmentation process by which the cloud breaks up into smaller clumps that become individual stars or small groups of stars, and understanding the interplay between rotation, turbulence, and gravity in molecular clouds is an active area of research in astrophysics. The stability of rotating structures depends on the balance between various forces, including gravity, which tends to pull matter together, and centrifugal effects, associated with rotation, which tend to resist collapse in directions perpendicular to the rotation axis, and in some cases, this balance can lead to stable configurations that persist for very long times, while in other cases, instabilities can develop that cause the structure to change shape or break apart. Rotating fluid bodies, such as stars or the gaseous components of planets, can develop instabilities that lead to the formation of patterns such as differential rotation, where different parts of the fluid rotate at different rates, or to the formation of vortices and other coherent structures within the fluid. And these phenomena can be studied both through observations of astronomical objects and through laboratory experiments and computer simulations that model the behavior of rotating fluids under various conditions. Computer simulations have become an increasingly important tool for studying rotation in astrophysics, allowing researchers to model the complex interactions between gravity, rotation, magnetic fields, and other physical processes in ways that would be impossible to study through analytical mathematics alone. And these simulations can follow the evolution of rotating systems over billions of simulated years, revealing how structures form and change in ways that can be compared with observations to test whether the simulated systems behave like real astronomical objects. The simulations require solving large numbers of coupled differential equations that describe how matter moves under the influence of various forces, and the calculations involved are so extensive that they require the use of powerful supercomputers running for weeks or months to simulate even a fraction of the lifetime of a star or galaxy. Yet despite these computational demands, simulations have become essential for developing and testing theories of how rotation arises and influences the evolution of astronomical systems, the resonances that can occur in rotating systems where the rotation periods or orbital periods of different components are related by simple ratios such as 2:1 or 3:2 can have important effects on the long-term stability and evolution of the systems, and many examples of such resonances are found in the solar system, including the 2:1 resonance between the orbital periods of Neptune and Pluto, and the 1:1 resonance between the rotation period and orbital period of the Moon, which is why the Moon always shows the same face toward Earth, having become tidally locked so that its rotation period exactly matches its orbital period. These resonances arise naturally through gravitational interactions between objects and can either stabilize orbits and rotations, making them more resistant to perturbations, or can lead to instabilities that cause significant changes over time, depending on the specific configuration of the system and the nature of the resonance between the largest galaxies and the smallest particles. There is a quiet space where motion is too slow to be noticed, where distances are measured in light and in time, where signals travel for years just to arrive. Atoms vibrate silently. Fields shift without sound. Energy moves through empty space without leaving a trace. Even in stillness, there is movement, so gentle, it feels like nothing at all. Time does not rush through the universe. It lingers around fading stars and newborn worlds. It drifts through empty regions where nothing seems to happen. Moments become eras. Eras become histories. Civilizations rise and fade. Mountains wear down into dust. Oceans shift and return, and within all of it, rotation continues, unchanged, unaware, far beyond what can be seen or measured. Paths cross, forces balance, systems adjust, clouds collapse and scatter, stars ignite and grow quiet, worlds form and wander, not because they must, not because they choose, but because this is simply how things continue closer to where you are. The room remains still. Shadows rest on walls. Air moves slowly around you. Your breath finds its own rhythm, in and out. No effort, no direction, no goal, just continuation. And now, as the universe continues its quiet turning, as stars, planets, and galaxies move without awareness, there is nothing that needs to be solved, nothing that needs to be understood. In this moment, rotation does not hurry. It does not pause. It simply continues. Light travels. Matter drifts. Space expands. Without intention, without concern. Let the motion remain ordinary, neither meaningful nor meaningless, just present. Far away, clouds of gas slowly turn, stars form, systems settle, and closer to you, your breath also follows its own gentle rhythm, in and out. Your body, like the universe, does not need direction, only time. Thoughts may soften, not disappearing, just slowing, like distant orbits, fading from view. There is no conclusion, no final answer, only continuation. And as everything keeps turning, without effort, without purpose, you may also drift into rest, not as an ending, not as a beginning, just another moment in an ongoing motion. Good night, and remain within the quiet rotation of the universe.